So thank you. For the last 20 years, I have been specializing on real-time physics simulations of complex machines in virtual environments. My own background is in theoretical and computational physics, and 13 years ago, we started a company here in Umeå as a spin-off from the university. And since then, we have invested some, I think, 200 years of development into our software and published some 50 scientific papers as well. And today we have a lot of customers around the world using our software for complex machine simulation. And though we're a small company, we sort of see ourselves as the market leader in this particular domain. And I will start by showing some videos to sort of illustrate what kind of systems we simulate. The first video, if you can see that, shows wheel loaders, construction vehicles, various types, excavators, forestry machines, cranes, rock drills, and many different types of simulators that are mostly used for operator training. So these are virtual reality training simulators. The second video shows a similar system, but for maritime applications, maritime engineering with cranes and anchor handling and so on. And the third video down on the left shows a subsea robot system, an ROV, that's doing robotic operations down deep in the ocean. And finally, the last video shows our technology integrated into ABB Robot Studio, where we simulate many aspects of robotics, including material handling, cable dynamics, and so on. We have actually not done that much in the field of AI and machine learning, but I guess we have sort of decided to change that now. So today I will show several projects that we have actually never shown before, and also some research results that are prepared for publication. So the topic of my talk is simulation to real from a physics perspective, which means that we start typically from a simulation. On the left, we have a virtual forestry machine, a harvester. And then we use machine learning to train a control system to make this system autonomous. And then we connect the machine learning controller to a real machine in the real world, and hopefully it works. And the gap we get there between the simulation and the real system would be then the simulation gap. We have done this much in the past and before, but for traditional control systems. So it's kind of similar, but also very different, because traditional control systems are very much human designed, and they are less sensitive to errors in simulations, whereas machine learning systems learn everything from simulation data. So there are two sort of basic technologies required to set up simulations like this. One is computer graphics and visual data, and I will not be talking about today. Instead, I would refer you to Jonas Unge, who is giving a talk about this later today. Instead, I will focus on dynamic simulation, the mechanics of these systems. In most cases, we work with deep reinforcement learning, although there are many other aspects of machine learning, of course. Then we start with a world description. So this could be a real world. In this case, it's an Epiroc scoop tram wheel loader in an underground mine shaft. So we read off state observations from this, and then we feed that into a deep network. And then we want that to map into control policies that give actions on this vehicle and makes it autonomous. In this case, we want it to be loading autonomously to fill the bucket and so on. I will come back to this. The learning is then directed using reward functions and many different types of methods. But basically, we use mathematics to define our goals, and then we use that for training. Simulation requires modeling, and our experience is that it's very important to start from simple models, conceptual models, and make sure that you can actually control this system to start with, because machine learning control is a fairly new topic, and starting with the most complex model at once can be quite a challenge. And then you gradually work your way and improve the physics simulations. And at some point, you achieve a model where you have basically the full I/O of the system. That means that you have all the control signals and the sensor signals that you have also in the real vehicle. And then at some point, you will have a model that I would call a minimum viable model, where you can start to iterate with real hardware. So this is sort of an agile modeling paradigm for machine learning. Time integration is a fundamental aspect of dynamic simulation, and in order to do it well, we have to understand the time resolution and the frequencies of the system. So we can estimate the time resolution by dividing the smallest relevant length scale in the system, lambda here, by the highest velocity of the system. And then we can sort of estimate the time step to be a fraction of this, say 1/10 or so. For many machine systems, this leads to a span between, say, 2000 Hertz for a robotic system, and perhaps as long as 50 Hertz for a big system like a ship at sea. However, information and internal forces in these machines travel at much higher speeds. In fact, they travel at the speed of sound. So if you have a steel construction, that means 3,200 meters per second, but also inside human tissue, you have high information propagation, 1,500 meters per second, roughly that of water. So if we want to model something seemingly simple as a human, 2 human fingers in a pinching gesture, and we put in the numbers, we end up with a rather extreme time resolution, 1/10 of a microsecond. So this seems kind of unreasonable. This is actually required to resolve propagation of forces inside the soft tissue. But it seems unreasonable because on these scales, nothing relevant happens with the hand and the fingers. So the question, how do we get around this? In fact, these problems only occur when we use explicit time integration. And I mention it because there's still a lot of research out there where people try to get this working, and it's very difficult. So instead, we turn to implicit integration methods. This means that we approximate the system to be rigid, and that corresponds to using an infinite speed of sound. That also means that we get global interaction in the system. And it also becomes sort of infinitely stiff. But we can relax the stiffness by introducing elasticity sort of backwards using regularization of the force constraints. But this also means that we need global solvers. We need to solve the entire physical system using numerical solvers. And this is one of the challenges that I will come back to. Furthermore, we have to handle the smallest, the tiniest timescales as well. So these can be seen in many trajectories as discontinuities. And even for a simple bouncing ball, it's a kind of a problem to resolve it because the bounce itself happens during a single time step. So then we have to deal with this using geometric methods to conserve momentum and energy. I will not go through the whole package of the methods that we use for this, but just mention that as far as we know, the best possible way to do this is to use variational integrators. That means that we do not discretize differential equations at all, because then we lose the symmetries. Instead, we discretize the most fundamental principle we know in physics, the least action principle. So we get discrete equations out of that. And the good thing about this is that even though we get discretization errors, we know that even those trajectories are physical trajectories. And that means that even though we have errors in the trajectories, when we use trajectories to do machine learning, we know that our machine learning system will learn physical trajectories rather than non-physical trajectories. And that's extremely important for the transfer. I mentioned the global solves. This is one of the grand challenges, to get scalability for really big systems and coupled systems and so on. And I'm going to show a video to sort of illustrate some of these challenges. It's a simple system. It's a deformable beam made out of jointed bodies. And we can change the material here from very elastic to perfectly stiff. And the stiffness sort of relation is 1 to 1 billion here. And we can also deal with impacts and frictional contacts. If we try to do this in an iterative solver, it simply doesn't work. The whole system collapses. And in order to get it stable, we would have to do hundreds of thousands of iterations, actually. Even with systems where we have less dramatic errors, as in this one, the errors that we are left with are non-physical. So that means that if we use iterative methods and we have remaining errors that are big, we get non-physical trajectories for that. And that gives us a different class of functions for the trajectories than we have in the real world. And that causes problems in machine learning. Actually, this also explains a little bit why you see so many dragons and rabbits and so on in computer graphics research that are made out of jelly. Because it's much easier to simulate jelly than to simulate something that is stiff. And unless you want to make your robot or your excavator out of jelly, you need to handle stiff systems. Furthermore, if you have models, you also need modeler parameters. And in general, you want optimal parameters for simulation to real, but you also want your machine learning system to be able to handle parameter spans. So that you can handle variations. And there are many ways of obtaining parameters. Ab initio means that you get them from tables, and periodic table, and material properties, and so on. But you can also do empirical measurements, and you can do model calibration against the real system. Of course, this only works if you have access to the real system. And I would say in the future, we expect engineers to first do things in simulation, and that means that they don't have any real machine system at all. You can also compute parameters from other models like finite element analysis for elasticity parameters. So if we look at an example, this is an ABB Yumi robot. For each body, there's a number of parameters you need to know. And there are 13 bodies and 12 joints. So you get 255 parameters. And if you don't really know these parameters exactly, but you want to vary them, then you get 10 to the power of 12 combinations. Now, this is obviously not practical. So fortunately, there are a number of methods now being developed, and this is one of the most active sort of areas of research for simulation to real, is how to set parameters in a smart way. And this also relates to machine learning itself. And I want to mention two papers. So one is by Muratore, Eilers, Ginger, and Peters this year. I guess that's the most recent result on Bayesian domain randomization of simulation to real. So that's a very smart way of mapping the phase space of these parameters into effective learning. And also another paper by Martin Wasser, Danica Kraljic, I think she's probably here today, Enrika Antonova, maybe she's here as well, using variational autoregularized alignment for simulation to real. So this means that you sort of use machine learning itself to find optimal parameters. So these are very important initiatives to get good simulation to real. Seeing is believing, so I'm going to show you some examples. This is an ABB robot controlled by a neural network. There's nothing special about the machine learning approach here. We're using vanilla PPO and 30,000 episodes and end-to-end learning. What is a bit special about this model is though that it has very high simulation to real for the traditional controllers. So when we use this with the ABB controllers, which means that we use a repeat program, a trajectory planner, and a model predictive controller as a regulator, then we have transfer, which is typically sub-millimeter precision on 2 kilohertz, and with variations that are smaller than between two robots of the same model. Now, I think an interesting question here is how far can you take machine learning for a system like this one? And even though there are like 10,000 papers out there, we still don't really know how far we can take machine learning when it comes to precision and performance. So this, I think, is an interesting topic and well worth a paper at some point. What about going beyond robotics then? Well, eventually all machines will become robots. But if you look at the research, I did a search here just a few days ago when I prepared this talk. So I searched for deep reinforcement learning, simulation, control, and then various keywords. And as you can see, robotics is totally dominating here. It's of course easier to have a robot in your lab than an excavator. So it's kind of natural to start there. But I expect that we will see a lot of work in the coming years that also goes into these other aspects of complex machines. But to do that, we also need better simulation methods. So I'm going to show some examples of that. So this is a preprint that we released this week, actually. This is starting from a high fidelity model with millions of degrees of freedom, which has been calibrated with empirical data. And then it's been reduced into a multi scale model for real-time performance. So it's roughly 5 to 10 times 10,000 times faster than the high fidelity model. A model like this can be used for many different things. Everything from like planning the bulldozing here, for example, with a very simple bulldozer. Bulldozing seems actually to be a fairly complicated problem. You can go on driving on like this forever and you still won't get any results unless you know what to do. But you can also use this, of course, for mechanical control. So you could basically do an end-to-end controller for this entire system. And we have also used this. This is from a project with Epiroc. What you see here is an Epiroc Scooptram ST18. So that's an underground mining wheel loader. And this is also a project funded with co-funding from Vinnova. The goal here is to read data from it and make it autonomous. So we read off video, depth camera, LiDAR, velocities, forces, and positions. And then we use agents, machine learning agents, to produce signals for the throttle, the steering, the tilt, and lift cylinders. And then we construct reward functions for optimal loading, energy efficiency, and to avoid wheel slips, and to make it safe and avoid collisions, for example. So this is work in progress, and we have a preprint coming up soon. Yet another example is a forestry machine. This is an autonomous forwarder. It's using a hierarchical agent system with reward functions for loading wooden logs. And here it's compared with a real system as well. In simulation, we get pretty high success. This is still early work. This is a master thesis project by Jennifer Andersson that was just finished a few weeks ago. And this will continue to do more sort of advanced control systems, and eventually we will also do it on hardware. What about systems and platforms then? Well, I will not talk about these. These are sort of products as well, but I will just mention some important aspects. One important aspect is that authoring is extremely important. It must be possible to get models into this. And to achieve this, we're actually developing now a new open modeling format for this. It's also important to have good 3D graphics and visual data. We do that by integrating with the largest platforms out there today, with Unity and Unreal. And we also integrate with the dominating tools for machine learning and control system. Everything ranging from MATLAB to PyTorch and TensorFlow and so on. And we also provide cloud simulation services so that you can run lots of simulations like this. And I think we will actually hear about a version of this used by Husqvarna in a while. I think that was really my presentation. I just want to close with some remarks that our software is now freely available for academic research within VASP. And we welcome collaboration on research and applications in VASP, in particular on machine learning for these model systems. I mean, we have these model systems running, and there are lots of people that could contribute to make them more autonomous and to do lots of research on them, in particular for the simulation to real transfer. And we're also interested in fundamental methods, both for simulation methods and for the machine learning methods. And we'd like to also see collaboration on the modeling formats and also on the platforms at large. And we're actually hiring. So if you feel like working for us, please contact us. Thank you.
Thank you. Great talk. Very interesting. So are humans still better than machines to drive these vehicles?
Yeah, I mean, the autonomous machines exist mostly using traditional methods and not so much with machine learning methods. So that means that you have very advanced and smart control systems. And then you can make machines very efficient. But then they are much like a traditional industry robot. They are programmed. Okay. So we don't know of any commercial systems out there using, say, deep learning methods yet. So I think this field is 4 or 5 years behind the automotive and road vehicles and so on. But it's really growing a lot right now.
Very, very nice. Thanks again. I didn't get any questions on the Q&A. So then thanks for a very nice presentation.
Thank you.